Hello students, good afternoon.
Good afternoon, ma'am.
Good afternoon. Today, let us discuss about PLL. I have given you introduction to the PLL. Okay, let me stress once again about the basic principle. All that. Okay, PLL, phase locked loops. Phase locked loops. This is a, phase locked loop. Okay, this phase locked loop. It is an important building block for many electronic systems where we have some feedback and all, or control, we can say. These PLLs available from 1930s onwards, right? These PLLs were there from 1930s onwards, but because of their high cost, because of their high cost, these were used for limited. Otherwise, these were not that much popular. Why? Realizing these PLLs is a bit costly affair, right? And therefore, because of their high cost involved in designing these PLLs using discrete components, these were not that much popular. Okay. Later, the IC technology, advancements in IC technology made these ICs available at inexpensive rate. That means these ICs are available, these monolithic PLLs are available at a lower cost. So therefore, because of the low cost, because they are available in the form of ICs with the low cost, they have become more and more popular. They are more and more popular. So therefore, we are going to learn about these PLL. Okay, phase locked loop, right? And then we have seen some, and that means this is like electronic frequency controlling. So what we have here is electronic frequency controlling. I'll show you that block diagram. You will understand what this frequency controlling is. Right. This concept is used in, that means these PLLs are used in satellite communication, then airborne navigational systems, FM communication systems, computers, etc. And I have also mentioned about some other applications which include these broad areas, that is frequency modulation, stereo decoders, FM stereo decoders, then motor speed controls, then tracking filters, then FM demodulators, then frequency shift keying, FSK decoders, like that. So many other applications, right? So TV or FM tuners, like that. These PLLs are used in several applications. And in this topic, that means in this fifth unit, what we discuss here is the basic principle of PLL and what are the various other different PLL ICs, and then some important applications we are going to study, right? So all this I have mentioned in the previous class. If we see this, this is the block schematic of phase locked loop, right? Introductory class I have just mentioned. Now I'll tell you with a little more, in a more detailed manner, I can say. So it has the few blocks. Actually, we say majorly 3 blocks. We say one is phase detector, the second one is low pass filter, and the third one is voltage controlled oscillator, right? So low pass filter, if it is a passive filter, then another amplifier is required. If it is an active filter, complete these two blocks together, one low pass filter is sufficient, because this is to amplify, right? If you design a low pass filter with if you design your low pass filter with ICs, that means active components. Otherwise, if you incorporate here an active low pass filter, then the gain also can be adjusted with this active low pass filter. So the the amplifier is not necessary. So the major basic building blocks of phase locked loop are the phase detector, low pass filter, maybe passive or active, and then a voltage controlled oscillator. Okay, so about each one of these blocks we are going to study in a detailed manner today, right? What are the different types of phase detectors? What are analog phase detectors? What are digital phase detectors? How one example for digital phase detector we will see today. Then a low pass filter. So what is this low pass filter? What is its role in PLL? All these we will see. Then what is this voltage control oscillator? Like that, each one of these blocks we are going to study in a detailed manner today, right? And if you see the basic principle of PLL, you just observe input frequency is applied here, right? So input frequency means we'll have some signal, right? Any signal, maybe any signal. Okay, so input signal with certain frequency is applied to the phase detector, and it will be having some output voltage here, right? Initially it may not be, later from the output, that means if there is no feedback voltage, it will be zero, right? So the phase detector will give output voltage which is proportional to the phase difference between the input frequency signal and the output of the voltage control oscillator, right? So the difference of these two will be available here, that is designed in such a way to provide DC voltage here, right? So the phase detector, other name to this phase detector is comparator. Other name to this phase detector, it is here what we use is comparator. Okay, so this comparator will compare input frequency with the output of the voltage control oscillator. So output frequency, and it will give the difference signal here. So this difference signal, we name it as error voltage. We name this voltage as error voltage. So if this DC voltage is applied to the low pass filter. So what this low pass filter will do, it allows all low frequency components to pass freely and provides attenuation to high frequency signal. Therefore, this low pass filter filters out all high frequency noise, and it will allow that low frequency signal to reach to the amplifier. If it is an active filter, filtration, the filter itself will, in the filter itself, we will adjust the gain of the filter. Otherwise, there is an amplifier required. And after that, finally, the output of the low pass filter is connected to voltage controlled oscillator. So I have mentioned what is a voltage controlled oscillator. So this voltage controlled oscillator is an oscillator. That means it gives frequency of the signal of certain frequency. And what is that certain frequency? That means it receives voltage from the low pass filter. So it gives output frequency. Voltage control oscillator gives output frequency proportional to the input voltage, right? So what is the function of this voltage control oscillator? It gives output frequency proportional to the input voltage. So if the input voltage is varied, output frequency varies. Okay, so finally the output of this voltage control oscillator is given here, right? So this comparator, again it will compare, and the different signal will be applied here, and this signal will be again passing through this. So this loop will be continued until we get what is that, error voltage 0, until we get error voltage 0, right? So in the next block diagram also, same block diagram, but the difference between this diagram and that diagram is here we are using what is that, passive filter. Next diagram, active filter is used. Okay, so let me show you this block diagram of basic PLL. Both are same, right? The circuit which I have shown just now, and this one, a block diagram which I have shown just now, and this one, both are same, right? So block diagram of basic phase locked loop or PLL. Okay. Now here you can observe what is F out, what is F in, all that. So this diagram is from our Ramakant and Gaikwad, and the previous one is from Rai Chaudhary. Whichever is convenient to you, you can learn and you can reproduce in the examination. Both the concepts are same. Right now, input frequency, then phase detector, low pass filter, then voltage controlled oscillator, VCO, voltage controlled oscillator. It is an oscillator which produces oscillations of certain frequency, and its input is the voltage. Therefore, we call it as a voltage controlled oscillator, and the output of this voltage controlled oscillator is taken as output. And again, this output frequency is fed back to the input for comparison, right? So now, if you observe this, from input to output, we call this path as forward path. Okay, so from input to output, we have these blocks. We call this as forward path. From output to input, we call this as feedback path, right? Output to input, we call it as feedback path. So forward path, we have 3 blocks, that is phase detector, low pass filter, and voltage control oscillator. In the feedback path, we have from output frequency to input output to input. That means voltage control oscillator output is connected to the phase detector through this feedback path. No other components are there. Okay. So output of the voltage controlled oscillator is connected at the input of the phase detector. Okay. So this is the basic block diagram. So here let us wait for a while and let us try to understand the basic principle of operation of this phase locked loop. Okay. So that is very important, because unless you know the basic principle, you cannot understand what are its functions. Okay. So let us once again discuss about the basic principle of operation of this phase locked loop. Okay. Now the phase detector, we also call it as the comparator, right? Phase detector, we also call it as the comparator. This comparator compares the input frequency that you want to take. Okay, input frequency with the output frequency of the voltage controlled oscillator. Otherwise, with the output frequency, we can say, right? This is the output frequency and this is input frequency. Therefore, this phase detector or comparator compares input frequency with that of the output frequency, right? Then what is the output of this phase detector? Output of the phase detector is proportional to the that means output of the phase detector is the DC voltage, which is proportional to the phase difference between input frequency and output frequency, right? So the phase detector gives output voltage as DC voltage. So how much DC voltage it is generating? That is proportional to the difference between proportional to the phase difference between F in and F out. Okay. So the output voltage of the phase detector is also named as error voltage. The output voltage of the phase detector is also named as error voltage. Why we want to compare these two frequencies, right? So why we call it as error voltage, you will understand a little later, right? Just a few seconds later, you will understand. Okay, now this error voltage is applied as input to the low pass filter. That means the output of the phase detector is connected to the input of the low pass filter, right? So what is the function of this low pass filter? This low pass filter, it allows low frequencies to pass and it removes high frequency noise, right? It removes all high frequency noise and it allows the output as I mean, it allows low frequencies to pass freely and it removes all high frequency noise. Okay. So here also the DC signal, right? You know, low pass filter cutoff frequency by any value. So very low signal, low frequency we use as cutoff frequency. So finally, this is also a DC voltage, we can say, right? Now then, this DC level in turn is applied. This DC voltage in turn is applied to the voltage controlled oscillator, right? Now, the input of the voltage controlled oscillator is from low pass filter. So that is a DC voltage. And depending on this voltage controlled oscillator gives its output as frequency, gives its output as frequency. That means input to the voltage control oscillator is voltage and output of the voltage control oscillator is frequency, right? It is an oscillator. So oscillator means which gives oscillations of required frequency. It may be 1 kilohertz or it may be 100 hertz or 10 hertz, whatever you want. So it will, which produces oscillations of required frequency. But it depends on what factors? Depends on the voltage that is applied. So we call it as voltage controlled oscillator, right? So this voltage, this voltage controlled oscillator produces F out, that means the output frequency, Now this frequency, that means the voltage controlled oscillator frequency, or this frequency is again fed back to the input of the comparator, input of the phase detector or comparator. Now, this will again it will give what is that difference signal. So this comparator will give difference voltage here, and that is again allowed to pass through low pass filter. Again, that is according to the difference between this error frequency, error signal will be there. So accordingly, the low pass filter will allow low frequencies to pass, and accordingly, the voltage controlled oscillator will give its output frequency. So this process repeats. This process repeats until the error voltage becomes zero. Until this error voltage becomes zero, right? So then what happens now? When does this error voltage become zero? When Fn is equal to F out. When these two frequencies are equal, then output will be zero. So therefore, we can say that this phase locked loop goes through three stages. This phase locked loop goes through three stages, right? So what are the three stages? That means the first one, it goes through three stages during this phase locking. So what is the first stage? That is called a free running stage, right? So first stage is called a free running stage, Then the second stage is called the capture mode or capture stage, mode, right? Then the third one is called phase lock stage, right? So third one is called phase lock stage. So like that, the PLL undergoes three stages, phase lock stage, right? So like that, this PLL undergoes three stages. First stage is pre-running stage, second one is capture stage, and the third one is phase lock stage, right? So what is this free running stage? When do we say that it is in free running stage, right? Now, when we say before you apply any input signal, before the input is applied, before you apply any input signal, the phase lock loop is said to be in stage one, that is free running stage. So what is free running stage? Before we apply any input frequency, this PLL is said to be in free running state. So that means before you apply any input signal, the stage of PLL, we call it as the phase locked, what is that? Free running stage, right? Free running stage. Then what is the second stage? Now without applying any input frequency, we call it as free running stage. Now what is the second stage of PLL, phase lock loop, right? Once you apply input voltage or input frequency, once you apply input frequency, then this VCO start class. Once you apply input frequency, then VCO starts changing. 1 second. Okay. So what is the next stage? That means what is the capture stage? So what is this capture stage means? Once the input frequency is applied, once you apply input frequency, then the VCO starts changing its output frequency continuously, right? So you can observe here, you are applying input frequency, then phase detector will give some output voltage, signal DC voltage, then low pass filter will allow those frequencies to pass, and then voltage control oscillator, based on the output of this low pass filter, voltage control oscillator will give its output frequency. Again, that is fed back to the phase detector or comparator. Now again, these two are compared, and at the output there will be, now error will be 0. So like that, error will be reduced. So like that, this loop is continuously repeating. So voltage control oscillator, it has given output frequency some value earlier, now some other value, like that until certain time. That means until the output frequency is equal to the input frequency, VCO is changing its output frequency continuously, right? So until the output frequency equals to input frequency, VCO is changing its output frequency, right? Once okay, this phase is called capture stage, right? This stage is called capture stage. So in the capture stage, what is happening? The VCO frequency is continuously changing. VCO frequency is continuously changing. To what extent it is changing continuously? Until it becomes equal to, until it is equal to the input frequency, right? So therefore, in this phase, the what is that? The PLL is said to be in what is that? Capture stage. Okay, the PLL is said to be in capture stage. So once in this capture stage, it is continuously happening. Once if the output frequency is equal to the input frequency, then the phase lock will be in PLL will be in phase lock state. Phase lock state. So like that, the PLL will be undergoing three states. Three states are three stages. First one is pre-running stage. That means without applying any input frequency. Then we call this PLL is in, this state is called as a pre-running state. Here, no input frequency is applied. Okay, then what is the capture stage? Once if you apply input frequency, then the output frequency will be changing. Then again it is fed back to the comparator, low pass filter, again voltage control oscillator will be changing. Like that, the output frequency is changing until the input frequency is equal to output frequency. So this process is called a capture stage, right? This is called capture stage. Once it is equal, then phase lock stage, right? Once it is equal, then the PLL enters into phase locked state. Phase locked state. So like that, now once it is locked, it will be tracking the input signal. So like that, the phase locking takes place. Phase locking takes place. So this is a repetitive process. Okay, this is a repetitive process. So like that, this is the, I mean, like that, the PLL will be working. Okay, input frequency is applied. Phase detector compares the input frequency with that of the voltage control oscillator output frequency. Then the difference error signal is applied to low pass filter. Low pass filter output is applied to voltage control oscillator. So this voltage controlled oscillator gives output frequency which is proportional to the input voltage, and that frequency is again fed back to the phase comparator or a phase detector or comparator. So in today's class, what we are going to learn is about each block we are going to study. That means this is just basic principle, right? In this basic principle, what all you explain, you will be drawing the block diagram. After that, 3 blocks you will be drawing, and after that, the figure shows block diagram of phase locked loop. It consists of phase detector or comparator, low pass filter, voltage control oscillator, then basic principle. All this, what all I have explained till now, you will be explaining, right? After that, about each block you have to explain. Then only you will get 7 out of 7, right? So phase detector. So what is a phase detector? It is nothing but a comparator. And here what are the different types of comparators? Like that, about each and every block we are going to study in today's class, right? So we will see that. And before we see, let us just have a glance on the basic block schematic of PLL is shown in figure, and it has a phase detector or comparator and a low pass filter and error amplifier. If it is a passive filter, if it is an active filter, directly you can say second block is a low pass filter, then the third block is a voltage controlled oscillator, right? So then before we go into the details of these each and every block, let us also have some idea on PLL in monolithic form, right? Monolithic PLL. That means I told you in the beginning, these PLLs are realized with discrete components earlier days, and because of the high cost involved, these PLLs were not that much popular, and therefore they were not that much used. Later, because of the advancements in IC technology, because of the advancements in IC technology, these PLLs are available in the form of IC at lower cost, right? Inexpensive. They have become inexpensive. They are available at lower cost. So this made these PLLs popular. So let us say this monolithic PLL, as I have mentioned, pin number 1 is minus VCC, and pin number 10 is plus VCC, and here we have last 4 pins no connection. Then these are the 2 input pins. These are the input pins to that means here we have comparator. This block diagram also I will show, right? The block diagram of this NERSC 565 I will show, right? I think PLL in general, till now what is the block diagram that we have seen is PLL in general, right? So after that, there are some PLL ICs available in the market. Of course, the first was Corporation. Later, many others, Motorola and others also have released some PLLs. And now we are talking about, as per our syllabus, we are talking about NERSC 565. Okay. So this is the voltage control oscillator output. Pin number 4 is VCO output. Then phase comparator. That means at the input we have comparator, no? So phase comparator VCO input. Phase comparator VCO input. Then a reference output. Then demodulated output. External resistor for VCO. We need some external components also. I mean, that means some external components are also connected in this 565 to this 565. So those components and purpose we will see later. Then 10th pin is VCC. So this is the PLL pin diagram. That means PLL NE or SE 565 available in monolithic form, right? So this is what about the pin diagram. And then we have seen these electrical characteristics of this PLL, right? Briefly, very briefly, I have mentioned, right? These electrical characteristics include operating frequency range, then operating voltage range, input impedance, output sink current, and output source current, like that. So many parameters. And this is available in 14 pin DIP and also 8 pin metal can, right? this IC 565 PLL is available as 14-pin dual inline package type IC and also 10-pin metal can type. Okay, and then some electrical characteristics of PLL 565. So here I mentioned that we have data sheet, right? So data sheet for any IC, any analog IC or digital IC, this data sheet provides complete data. Just a sample of it I have mentioned here, right? If you want more details, we can also search in internet for the data sheet. Okay, so data sheet you need not mention fully in the examination as a student, right? Because so many ICs are there, many data sheets are available. For each device, one data sheet is available, right? That means for each device, data sheets are available and they give full information like what are the different package types it is available and what are the suitable applications, for what type of applications you can use this IC and what is its internal diagram, what are the various operating frequency range, like that. So many other parameters are mentioned by this data sheet. Okay, so just as an example, I have mentioned very few. If at all, if it is required, some general points only I have mentioned. You please remember this. Operating frequency range is 0.001 hertz. That means almost like 0. Okay, so 0.001 hertz to 500 kilohertz. That is the operating frequency range of this PLL 565. PLL 565. Then operating voltage range. Operating voltage range is plus or minus 6 volts to plus or minus 12 volts. Then input impedance is also high, 10 kilo ohms. Output sink current is 1 milliamperes and output source current is 10 milliamperes, like that. So like that we have some electrical characteristics of this 565 PLL. Okay, now a 565 block diagram. Just now what we have seen, the general block diagram for any PLL we have seen. Now this is the block diagram of 565 PLL. That means only this IC is block diagram, right? So I think you are able to understand the difference between the previous block diagram and this block diagram. Previous block diagram is, in general, any PLL has a phase detector, a low pass filter and a voltage controlled oscillator. So this PLL is designed with the same blocks, right? With the same blocks and some additional external resistors are there, right? External resistor and one capacitor, like that there are some components connected. So this is the block diagram of PLL, right? So whether it is the block diagram of PLL or that means it is a general block diagram or NERSC 565 block diagram, blocks are same, right? PLL phase, phase detector, then amplifier or low pass filter and voltage controlled oscillator, right? So therefore, just write for this block diagram, right? 2 and 3 are the input pins. Just now I have shown you the pin diagram. 2 and 3 are the input pins. Those inputs are input to the phase detector. Input to the phase detector. Now phase comparator VCO input. Phase comparator VCO input is pin number 5. Output of phase detector is connected to either error amplifier we say or low pass filter we say, and it is connected to low pass filter, and output of this low pass filter through a small resistor it is connected to demodulated output, one pin number, and pin number 6 it is the reference output. If you observe, the output of this low pass filter or amplifier is connected as input to voltage control oscillator, and this voltage control oscillator gives its output at 4th pin. It gives its output at 4th pin, right? Then other 2 pins plus VCC and minus VCC, they are connected here, right? Pin number 8 and pin number 9 and pin number 1 is plus VCC, minus VCC, and pin number 10 is plus VCC. Here it is pin number 10 plus VCC, and pin number 8 one resistor R, and pin number 9 one resistor, one capacitor C. So this is the basic block diagram of PLL. See, pin number 10 is shown here. That means this is connected to pin number 10. Okay, up to at the top of pin. Okay, plus V6. So like that, this is the basic block diagram of 565 PLL. 565 PLL. Right. Now here also we understand that one phase detector and comparator, and one low pass filter or amplifier, error amplifier, and voltage control oscillator. Therefore, by understanding that there are same blocks, we shall also learn about each one of these blocks now after just learning what are the applications of PLLs. So PLLs are used for frequency multiplication and also for division. PLLs are used for frequency multiplication and also for frequency division. And this can be used as a frequency translator, right? PLL can be used as a frequency translator, right? Frequency translation means from one frequency to other frequency, it can be translated. So all these applications in a specified manner, that means very specifically with respect to circuit diagrams, we are going to study in the next class, right? What are the applications of PLL? So I think your yesterday question paper, we have seen what explain about the applications of PLL for PLL as a frequency multiplier and PLL as frequency translator. Like that, two questions I have seen. So we'll study all these five. Whatever question we get in the exam, we can score our marks. Okay, the third application is AM detection. PLLs can be used for AM detection, and PLLs can be used for FM demodulation or detection. Then FSK demodulator or detector, right? FSK demodulator or detector. I think using 555 timer, we have seen FSK generation, right? So FSK generation, and those details we study again here when we talk about FSK demodulation. Okay, so having this much knowledge about the applications of PLL and its block diagram, and what is PLL, what are the basic what is the basic terminology used, what is the basic principle of PLL. Now we shall discuss about each one of these blocks. Okay, each one of these blocks. The first block is a phase detector. Phase detector. So what is a phase detector? Right. I have mentioned that phase detector, it is nothing but a comparator. It will compare two frequency signals. Now, specifically, let us see, there are different types of phase detectors. One is analog phase detector. Second one is digital phase detector, right? Analog phase detector and digital phase detector. So one example for analog phase detectors is a double balanced mixer, right? A double balanced mixer is one of the examples of analog phase detector. And if we see digital phase detectors, there are different types. One is exclusive OR phase detector. That means exclusive OR gate is used. Then the second one is edge triggered phase detector. The third one is monolithic phase detector. Monolithic phase detector means IC such as the 4044 IC is used as phase detector. Okay. So like that, there are different types of digital phase detectors, and keeping all these in mind, we are going to study about the exclusive OR phase detector. Exclusive OR phase detector. You know what is an exclusive OR gate? So let us see. This is an exclusive OR phase detector. That means for this phase detection, exclusive OR gate is used. That's all. That's why we call it as exclusive OR phase detector. You know what is an exclusive OR gate? Actually, this is an exclusive OR gate IC CD4070. It is a quad. It is a quad 2-input exclusive OR gate. Quad 2-input exclusive OR gate. So what do you mean by quad? 1, 2, 3, and 4. 4 exclusive OR gates are there. That's why the name WAD. What type of exclusive OR gates? They are 2 input exclusive OR gates. Pin number A1 and A2. A1 and B1 are the 2 pins, input pins. Output pin is Y1. Again, A2, B2, output is Y3. Right? VSS, that is pin number 7, and VDD is pin number 14. Then what is that? Four exclusive OR gate. So 4 outputs and 8 inputs, right? 8 plus 4 outputs, 12. 12 plus VDD and minus VSS. VSS and VDD, 12 plus 2, 14. So it is a very simple IC, right? That is the difference between analog ICs and digital ICs. Digital ICs, just input pins and output pins. If you follow notation, that is sufficient. Just you can remember these pins very easily, right? 7th and 14th VDD and VSS, and then input pins and output. Whereas analog IC means discharge pin. What is that? Modulating, control voltage pin, then discharge pin, then VCC pin, ground pin. Like that, so many will be there. Here, inputs and output. VCC and ground are VDD and VSS. So this is an IC, and VDD can be applied from 3 to 15 volts, DC, and VSS is a ground point. And you know, last class we have mentioned, I remember. So what is VSS and what is VDD? Drain supply and source supply voltage, we say drain supply voltage is VDD and this is ground. Okay, okay, we call it as ground because it is CMOS. If it is CMOS, we'll have plus VDD and minus VDD. Otherwise, this VSS is minus of plus VDD. Okay, so this is an exclusive OR gate. Now, all are identical gates. Therefore, let us take one gate. So out of 4 gates, we are taking one. That is 1/4 of 4070. That means 4070 is a WAD 2 input exclusive OR gate. Out of 4, we are drawing one exclusive OR gate here. That's all, right? So what are the inputs to exclusive OR gate? F in, F out, right? That means from the output of the voltage control oscillator we get. So we are talking about detector only. Detector, it is comparing input frequency with the output frequency of the voltage control oscillator. So these two are applied to exclusive OR gate. Then what is the output that we get at the output of the exclusive OR gate? And let us have a glance on this truth table, right? We have inputs and outputs. Inputs are named as A and B, and output is named Y. Both inputs are low, output is low, and when both inputs are high, output is low. But it is an exclusive OR gate. That means input and output. That means both inputs are different. That means when we have exclusive inputs, we will get output high. If we have same inputs, output is low. If we have same inputs, output is low. But if the inputs are exclusive, then output is high. That means when it is low and low, output is low. When it is high and high, output is low. But when one input is low, other input is high, exclusive, therefore output is high. When one input is high, one input is low, then output is high, right? It is an exclusive OR gate and its logic diagram. I need not stress this much. Also, you know what about this exclusive OR gate. Okay. Now let us see this type of waveform. That means till now you know low high. Otherwise 0 1. All this you will be doing, right? 0 0 0 1, and then 1 0, then 1 1. All that you will be knowing. But now if you observe the waveform, this is F in input frequency waveform, one square wave, right? This is one square wave. Then output frequency waveform, there is some difference, some phase difference is there, right? Therefore, with some lagging, output waveform is also same as input waveform, but there is some difference. There is some difference, phase difference, and therefore output is like this. Okay, now output means F out, another input to exclusive OR gate. So these two are applied to exclusive OR gate. F in and F out are applied to exclusive OR gate. Now, what is the output of this exclusive OR gate? Right? You observe. Let us take the first part. Let us observe this one. Right? This difference is phase difference. Right? It has started at t equal to 0, and the other input has started at t equal to 0 plus some phi. Phase difference is there. So now, if you observe this area, if one input is high, and the other input to the exclusive OR gate is low, and therefore exclusive OR gate output is high. Exclusive OR gate output is high, right? Because one input is low, one input is high, other input is low, therefore output is high. And if you observe here, one input to the exclusive OR gate is high, other input to the exclusive OR gate is high, and during this period, when both are high, output is low, right? And here if you observe, one input to the exclusive OR gate is low and other input is high, so the output is high. So like that, these two waveforms, that means a series of pulses, right? This square wave is continuously applied to the exclusive OR gate, then continuously the exclusive OR gate will be giving the output voltage like this, right? So VDC is the VDC equal to output voltage. So it is for 0 phase difference, right? Then pi, 2 pi, 3 pi, 4 pi, like that. What is the phase difference? Otherwise, what is the output is waveform at the output of this exclusive OR gate is given like this. Okay, so this is F in, this is the square wave, right? And F out, another square wave with some delay. So accordingly, the output waveform will be like this. Okay, so this is the exclusive OR detector. Okay, now this comparator or detector, what it will do? It will produce the output voltage. Comparator output is DC voltage, I said. Okay, so this comparator gives output voltage proportional to the phase difference between F in and F out. So proportional to the phase difference between F in and F out, the detector will be giving its output voltage from VCC to ground, 0 to VCC. If there is no phase difference, the output voltage will be 0. If there is some phase difference of pi by 2, then output of the phase detector will be VCC by 2. At pi, it is maximum VCC. So like that, the phase difference is found out, and proportional to the phase difference between F in and F out, the comparator will give its DC voltage as the output. So like that, the phase detector will give output voltage proportional to the phase difference between the input frequency and output frequency. So this is what about block 1. This is what about block 1. Then what is block 2? Low pass filter. Low pass filter. So we know about the low pass filter. The basic block diagram of PLL has 3 blocks. One is phase detector, second one is low pass filter, the third one is voltage controlled oscillator. So just now we have seen a phase detector. So you have to, while explaining, you have to include all these. Okay, so only when they ask if you want to explain, you will be losing marks. Okay, draw the block diagram of PLL and explain the function of each block. Then you have to draw the block diagram. You have to list out what are the basic blocks you have. Then after that, you explain about the basic principle. Then about each block, like this, what all I am discussing now, you have to write. Okay. Now let us see this low pass filter. We know low pass filter very clearly. We have studied about this low pass filter. This is one what we say passive filter. This is another passive filter. And in our unit 4, we have studied about active low pass filters. So the same active low pass filter, what we have studied there, you can draw, right? Because we know very clearly about that low pass filter. This and that both are same. It is up to you. Okay. Then what are the additional points that you have to write? Input from phase detector is the voltage represented here, and the output of this low pass filter is given as output is given as input to voltage controlled oscillator. Right? So like that, the output is given to voltage controlled oscillator. So all other things are same, but additionally, this low pass filter has some what I can say, some most important functions also. Right? Let us see that in the next slide. So this low pass filter controls the dynamic characteristics of phase lock loop. Right? So what are the other functions of low pass filter here? So this low pass filter controls the dynamic characteristics of phase locked loop. Okay. Then what are the dynamic characteristics of phase locked loop? Okay. So what are the dynamic characteristics? Means the capture range, the lock range, bandwidth of the PLL, and transient response. So here we have to know what is the capture range and what is lock range. Right? We have to understand what is capture range and what is lock range when we talk about the dynamic characteristics of PLL. Okay. So the lock range, it is defined as, when we say range of frequencies only. So it is defined as the range of frequencies over which PLL system, the lock range I am talking about. Okay. So lock range, it is the range of frequencies over which the PLL, system, the lock range is defined as the range of frequencies over which the PLL system follows the changes in input frequency, follows the changes in input frequency. So that is called lock range. That is called lock range. Otherwise, we can say this is the tracking frequency, we can say, right? So therefore, the other name to this lock range is tracking range. You can also call it as tracking range. So the lock range is range of frequencies for which the PLL system follows the changes in the input frequency. When the input frequency is changing, your PLL is also changing. PLL system is following that changes. Okay, that means it is tracking those changes. Therefore, this is also called as tracking range. So lock range and capture range, these are controlled by our low pass filter. Low pass filter controls the dynamic characteristics of PLL. Okay. Then the next term is capture range. Right? What is the capture range? The capture range is the range of frequencies. Again, right? It is the range of frequencies in which the PLL acquires phase lock. Right? So this is the range of frequencies where PLL acquires phase lock. Right? That range of frequencies is called phase lock. Right? That range of frequencies is called capture range. Capture range. So this is about capture range and lock range. Right? All these dynamic characteristics are controlled by our low pass filter. Controlled by our low pass filter. The third block of this PLL is voltage controlled oscillator. Voltage controlled oscillator. So this is voltage controlled oscillator is available in monolithic form. It is a 566. It is also its pin number. This IC number is 566. Voltage controlled oscillator. So this voltage controlled oscillator, it is available in IC form, and to this voltage controlled oscillator, input is given from the low pass filter and output is at the output we get output frequency, right? So input is a voltage, output is a frequency. So input is obtained from low pass filter and output frequency proportional to the input voltage is generated by this voltage controlled oscillator. Now if we see this voltage controlled oscillator connection diagram, right? So pin diagram is different and connection diagram is different. So pin diagram means only pins we will mention. Connection diagram means the internal connections you can, external connections you can observe. This is the connection diagram of VCO, voltage control oscillator. This IC is also introduced by Synetics Corporation. Okay, so then this, if you observe this VCO connection diagram, pin number 1 is ground, and then we have 3 and 4. These are the outputs, whether it is a square wave or a triangular wave. These are the outputs. Then you just observe some other components, 2 resistors, 3 resistors, and components R1, R2, and R3. So this is the voltage control oscillator connection diagram. Okay. Now this voltage control oscillator, that means which is available in monolithic form 566, its maximum output frequency is 500 Hz. Its maximum output frequency is 500 Hz. That means it can generate for NA or SC only. If you want to obtain higher frequencies, higher output frequencies, you can also use other manufacturers' VCOs. They are Motorola's MC4323 and MC4024. Right? You can also use this voltage control oscillator. So many other manufacturers also produce voltage control oscillators. Okay. So all this I want to say, and with this I want to say thank you all for your patient listening and be online, and I want to take your attendance also, right? Let me take your attendance. Only 47 students. I know out of 62, only 47 students. Let me stop recording. Yes.